Yeah.
I can start.
Yes, please.
It's a great pleasure to introduce today's speaker, Professor Nouri, Fatma Zohra. Professor Nouri received her early training in mathematics in Algeria, followed by advanced studies in the United Kingdom. She holds a DOS in functional analysis from the University of Annaba, completed the joint matriculation board in the UK, earned an MSc in modeling and numerical analysis from the University of Oxford, and obtained her PhD in applied mathematics jointly between Oxford and Strathclyde University in UK. Professor Nouri has been a full professor since 2000 and was recently appointed distinguished professor in March 2025. And this reflecting her contributions to research, teaching, and academic leadership. Professor Nouri's research spans several major areas of applied mathematics, including mathematical modeling in biology and medicine, numerical analysis of fluid mechanics and porous media flows, PDE-based image processing, multiphysics and coupled problems, as well as stochastic modeling and data-driven methods. And today, Professor Nouri will speak about mathematical modeling and application in cellular systems. Thank you, Professor.
Thank you, Abdulkader. I start by thanking the organizers for this very fruitful events for seniors and also PhD students. Thank you very much. بعد بسم الله الرحمن الرحيم. Today, I would talk about mathematical modeling and some application. And my outline would be the motivation. Why do we need mathematical modeling nowadays? I will just set up some results and models from different applications and experimental sciences. And then I go deeply to give you some analysis on cellular systems and tumor growth with results numerically and theoretically. So we start by why do we need modeling? So we need it just to spare time for experimentalists. And then because of the cost, and the cost, when I talk about the cost, I talk about it money-wise and also time. And I will give details on that in due time during my presentation. Also, the absence of data, and this is quite costly, or also we don't have facilities to do this. Error in measurements, and this is all the tools we use it for measurements can also not be very satisfactory. Prediction, we need to predict some solution in short-term time and also preventing disasters, especially in industry and some other and medical science as well. To do the modeling, we need ingredients. When I used up to now to teach numerical analysis, I keep telling them any method, it's like a recipe to make a cake. If you forget one thing, you're lost. So the ingredients for mathematical modeling would be to know the medium, because we are dealing with some such phenomena or different phenomena, and each phenomena has its own particularity. We need physical laws, we need parameters, variables, and what we need also data, which is not always available. We need conditions from the data, and in mathematics, mainly we need initial and boundary conditions, which they take them from the data. Then the methods would be mainly use methods to know how to set equations, to set the systems we know to deal with. Mathematical equations would be ODEs, ordinary differential equations, or PDEs, partial differential equations, could be algebraic equations as well. And this could be in deterministic or stochastic matter. once the equations are set, we have to go through the mathematical analysis. And one main thing is the well-posedness, the existence and uniqueness of the solution, which not very well known for experimentalists or experimental sciences, because they only want to see the results, especially simulating results. But for us, as a mathematicians, applied mathematics, we do not know how to simulate, how to find the right methods to do the simulation unless we have some theory set behind. And for the well-posedness, we can do it in strong sense or weak sense. And I'll give the details during the presentation. Or when things do not work properly for us, when the problem is not well posed, we need to do something about it to cure it. That's regularization. Then once everything is fine, mathematically or theoretically, we go on and do some numerical analysis in a theoretical side, or just to find what kind of methods we can use. We need to find the suitable and efficient schemes to solve the problem. And this needs to be done through stability, consistency, and convergence. This is theoretically. And then just go on coding and simulate the problem. Once we get the results, we have to validate it. Validating is confronting it to the experimental data or the results from the experimentalists, or calibrate it. We have to change or adapt things to make it better. Okay, let's start with the first application, with the pollution in surface water, which is a very important problem, especially for nowadays life. And this pollution can affect the human society very, very highly. And the pollution can be taken from the air we breathe, the soil we grow our food, from the water, especially what we drink. That's why we say this place is contaminated. Don't drink from such place is contaminated. Nowadays we have what's it sold even as a water, but still we don't know what's inside. So the water and soil pollution, it happens when the chemicals, especially when we use fertilizers, pesticides to kill the insects, sewage, all this bad water that it goes straight to lakes or sea, etc. While the air pollution, we know very well it comes from the release of harmful gases, comes from vehicles, power plants. As you see on this picture, for example, they are just pushing all this pesticide on the soil that we grow the food. And here we have both the air pollution and also the soil pollution. On this side, sewage, the eaux usées, the sewage just goes on the seas. Here in our country, they just do and then sometimes they stop it during summer, during the swimming season. And here is the industry. And I live in a very highly polluted place, Anaba, where they release all the industrial effects there. So in the pollution in the water, particularly, the main element is the oxygen. And we know that the oxygen, we just uptake it from the atmosphere, but when there is contaminated waters, there are what we call the microorganisms or bacteria, which break down all the organic matter in the water. So we lose that what we call here the BOD, which is just the biochemical oxygen demand. So we need this oxygen. But the diluted oxygen in the water would be taken by these microorganisms, and that's why we have very contaminated water, and we cannot really, which is harmful, we cannot drink it, or if we drink it, we have health problems. So now this is just the background of the problem. And the first model that has been set up in Ohio Lake in Japan was by Streeter and his colleagues in 1925. And later on, it has been developed by others, among others, Professor Bernardi, may she rest in peace, and myself through a proper project between France and Nigeria for like 5 years. We worked on this original and also developed models, and we set up a model treating this kind of problems. And lately, Lachache, he submitted his thesis on other two developed models in different fields. So here, go back. No, I just set up this. The main thing we need is the BOD, the biochemical oxygen, and also the diluted oxygen, or the concentration of that. We go to the mathematics. We have to set all what we need in the mathematics. We need always a space to work in. Here, let's take an omega to be a bounded game with the Lipschitzian, of course, with a very regular boundary, whether in 2 or 3, and then write down this set or this system of equations where D here, usually we take it as a diffusion, but here it's dispersion because the bacteria is dispersed in the water. Okay, it has the same effect like diffusion coefficient. We have the B, that's our first unknown, which is the biochemical oxygen demand and the concentration. We have 2 rates related to the concentration, the diluted oxygen, and also the BOD related to B. And the first data, of course, we did always some data. The data is just the pollution here, the uptake oxygen from the atmosphere, and these are the boundary conditions. And you may note here, we don't have any boundary condition on B, which is very hard to measure. This is from the experimentalists from hydrogeology and engineering. They say that we can measure the concentration in the water, but not the biochemical oxygen demand, or sometimes it takes so long. As I said at the beginning, the cost is always something that pushed the experimental researchers to go to modeling. Okay, so one principle, one thing we should do, not just solve this system. This system, it looks like linear and simple, but I will tell you that when you go on analyzing it, it's not that easy. It's very hard, we have to regularize things, etc. But one thing here is just to determine the boundary condition on B, knowing this known F, G, and alpha and beta, which is also an extra work to solve this system. So, well, all the analysis, I'm just giving a brief results on that. Once we analyze the problem and also try to regularize one thing that doesn't work, etc., we go on resolving this problem. And we solve this system of equations to get some results. So this is our domain. And the domain, you see, it's a bounded, very regularized boundary condition, sorry. It's just from photos. This is the Zohra lake in Hannaba. We can also work on the lake of Le Mans in France, which is a very polluted place, and then solve this problem. This always the R's, which is these rates, are given by exponents. We just plot them, and we took some oscillating discontinuous because they are like that, naturally speaking. So either we do some interpolation from the data, which is a table, or just write down the equations for them. We solved it on this meshing, which is a little bit coarse meshing. Here's a finer, just to make a better result to see, because we need a finer mesh and finite elements to solve this discontinuous oscillating coefficients. And then the solution BH and CH. And we see it was very stable. We had some good results. It was satisfactory to give them to the people who need them. On that side, I just give, without giving details, I just give this equation, which also treat the transport of pollutants in the Mediterranean. This is a real problem. And what they do, the engineers, they measure the pollution somewhere, especially when there are some release of industrial waste, and then write down the system and try to see the evolution of this pollution or pollutants in that region. And you see after a few iteration or after a few times, you can see that this pollution, at this point, because they measure at different points and then they look everywhere. If you just take one point, it started with, just put this where here. If we start with a very small amount of pollutants and see the evolution of it, we can see that this pollutant is getting more and more. And can you imagine if we take more measures on this, just this part of Mediterranean, you can imagine how things polluted, whether for swimming or I don't know, nowadays you see like we take out the salt from the water to make it drinking water everywhere in the world. So this is very a special issue and very important issue for us. The second problem, I would give the model of something taking in medicine, and it is stem cell therapy or the therapy by stem cell. And this problem, we treated it in the study group in UK in 2012, where the orthopedists just from Kiel Hospital, that's in UK in the north, they just presented what they want to do. Well, you know, stem cell is well known nowadays as a therapy for reparative medicine. And they do it either by direct injection of these stem cells, which they culture it in a special labs, or they implant it with surgery. With these two methods, there is always limitation. There are always some inconvenience. And the inconvenience of both methods is that the location is not accessible. You may have non-accessible, so you need to do surgery many times, or also you have many sites of what you want to cure or this repairing. And also you need repeated dosage. Or if somebody has, I don't know, defect intervertebral, they just do on one part and then do it again, another part, etc., until they finish the work. And also they may not have candidates for surgery, and this is for the cost. It does cost a lot, or it's also very painful. People cannot do it twice a week or twice a month or twice a year. It's still very painful. So the patients may not accept to do it. They submit it from the suffering. They just say, okay, I'll keep having this. So we got some data. These are the two doctors who brought at that time the data to work with. And they said, we are thinking, since 2009, they were thinking of using what you call magnetic stem cells. Instead of doing it directly, injecting where it should be, or do implantation by surgery, they said, we thought about something else, which is magnetic stem cell. And they explained to us what are these magnetic stem cells. They try to culture something like magnetic particles as a particle, and they inject them, but it didn't work that way. But they said, okay, we just want to deliver or direct these MSCs to their intended sites by using lumbering. And this lumbering is just something magnetic. what they do, they implant a magnet and the skin of the patient, and then use this magnet to direct it to just attract these cells. So for the literature review, some people worked on that for other issues, and we, before starting to work on any phenomenon, any problem, we have to look to something to start with as a base of work. And either they use the poison, of course, this can help to help, the fluid flow, which is the blood flow, to push the cells, and or advection diffusion, because there is a diffusion on the other side, something to make things move, the motion of the magnet part in the bloodstream. And then we started in that pluridisciplinary group, are different, mathematicians, physicists, chemists, pharmacists, medical doctors, biologists. So everyone has his own worry. So we start asking maybe naive questions at the beginning, and we say, okay, we want to understand how this magnetic field that you put under the skin to direct the cells can compete with the blood flow, because there is also a velocity of the blood flow, and how this cell motion could go in different vessels, because the vessels don't have the same shape, the same size. They have different sizes, different shapes, etc. Another question would be, is there an optimal number? The optimality is a little bit mathematics. Is there an optimal number of these cells to be injected or via the vessels? And also, what is the proportion of these injected cells that reach the target? We injected, not know how many of them, and how many of them reach the target. Another question would be, how long does it take to reach the target? And also, what is the length of time the external magnet should be used? Or this question would ask. And then we end up by thinking, okay, there are two main things: the action of the fluid on the cell, which is the blood on the cell, and the cell in the blood. How can we deal with that? And we end up by having an idea of a system of two equations, the Newton-Euler, with the right-hand side taking into account the hydrodynamic force acting on the surface, because there is this magnet and it's on the surface, that's underneath the skin, and also inside the vessel where the cell is moving in the blood. And this can go in fluid mechanics or dynamics by Navier-Stokes. So we started to do this, analyze this system of equations, and then do the numerics and also on. But we had some instability. That's what I could explain to that as I was doing the numerics for them. And I said, okay, it looks so unstable. I don't know, something just doesn't cope with the theory we were tracing. And then I said, of course, we are using the free FM with finite element, which are very stable. This should work, unless we have to compute or remesh the computation domain, because there is a moving. So, and also the cell is very fluffy. It's just not rigid. It's not something rigid that's moving inside the blood. So this would not really work properly. And doing remeshing the domain is not an easy task to do. Then the medical doctors, Kimpton especially, were saying, okay, do you want to know how does it look like, this cell they are making in the lab? So we went to this lab, we looked at it, it looks a little bit fluffy, something like a fluid. And we asked him, okay, is this cell can be taken as a fluid? I said, yeah, but not like the blood. So we said, okay, we know how to deal with multiphasic phenomena, and this would be a biphasic model. we took the blood and the cell. Here I put a bubble just to show you that is something that is very fluffy. So we considered two fluids with different densities because they're not the same nature and different viscosities using just Navier-Stokes equation, just one Navier-Stokes equation, which is well known, and we used to deal with that. So you see here, this is the Navier-Stokes equation. U is the velocity, P is the pressure, F is just the data, the given data. But usually, but just row, not a row of dependent of this function, or mu is the viscosity, which doesn't, we never used it as dependent of some other function. Of course, it could be dependent of the space variable or the t variable, but no. But because there is a motion, so it has to depend of the motion of this cell. And adding a transport equation, and which is well known, we call it the level set function, which is a solution of that. Solve this and put it inside that, and then keep going on and off, solving these two set of equations. And then, of course, we have to know that the density when we are in the fluid, in the blood, is going to be different from the bubble or the cell, and the same thing with the viscosity. And this work, the report in this, you can find it here. Well, let me just explain this. Well, it should be written here, but because we had some problems with regularity, we just regularized with the Heaviside function. And then because the thickness of the interface between the cell and the fluid it's a little interface, but still we have to take it into account. So we just split it up, the work between inside the cell, in the blood, and in the between. So this is a term of regularization, which is well known, and we use it a lot in image processing. Okay, our velocity would be written in this way. It's between the blood and the cell, and lambda is just the strength of this magnet we put underneath the skin. So when we take lambda equals 1, that means that we just count on the velocity of the blood to push the cell. You see it, he's pushing. And we put in the second experiment the magnet in the middle of this domain. We just took this rectangular. And then you see, I think lambda was 0.35 or something, a little bit less than half. And then you see that the cell is pulled in this region. And then higher, when you make it higher, we're just using adaptively. We didn't have any data on this magnet, and you see it's pushed. So these results were quite satisfactory for the doctors, but still we're just working with one cell, which is not reality. Okay, later on, after the study group finished, we only worked for 1 week, really, all the time, all together. I tried to do the numerics for them for 2 cells. That was 2014 or something. I kept really dealing with that because the analysis changed and everything. And then with a low magnet, things just, they're both pushed a little bit there. But when I make it a little bit higher, one is pushed there and the other one was pulled out by the other one. This one goes there and it pulled the other one. I could only explain this to them by numerical instability, because there is numerical instability coming from the computation. But I don't know how to explain it better than that. But this problem is still under consideration, because if this works, we can go further with many cells and see how it happens. The third model I would like to I would like to explain today or present today is something from pharmacology. And this work was done in AstraZeneca, also in 2015, I think. And they were keen or putting in commercialization antibodies, but not, in a particular way. So I can tell you in Britain, they never give you a prescription with more one medicine. They only give you one medication. And to cure specific diseases like people who have cancer or chronic diseases, they cannot give them something uh, very strong or too, etc. So they were thinking, okay, if the antibiotics don't work, we may go to antibodies, but this antibody we can only give one. But in case they have more than one disease, can we put up or set up a multi-specific antibody? And they started to think about the bispecific, like somebody who's have a problem with cardiology and he has a cancer. What if the immunity just be very low? How to deal with that? And thinking about that, they say this would be a very potential therapeutic if we can do it. And from the point of view engineering, because it's medical engineering, because I think in a very to say high standard form of these antibodies to be put. And they said, okay, if we can work on a bispecific antibody just to be capable to bind two antigens. And with this in mind, they say, okay, explaining to us as a study group, a pluridisciplinary study group, our goal would be targeting therapeutic to specific disease processes. They want also to mobilize additional arms. It's like this antibody would have an extra arm to attack other more than one disease. And also, if we put up a bispecific antibody, the dual specificity compared to the monoclonal antibody would be highly affin. So this affinity of two arms, at least, would be something really clever to do. And also crossing linking cell surface receptors would also give something novel in biology for a potential therapy. These are real pictures or photos of the antibodies. That's how it looks like. On that side, it's an antibody which should take into account the target A and another target B whatsoever. So we don't talk about specific diseases. And on that side, this is the bispecific they want to put on and cure more than one or curing some disease process. As you see here, the half part is the blue, which is that one, and the other one is the half part, which is purple on that side, and combining the two to get a bispecific targeting A and B. Okay, these are just the setting to write down our system of equations. We have to think about the antibody in solution, the amount for targeting B, surface A, and also targeting both of them, and putting this into mind and write down the equilibrium or the physical law for that, we end up by having this system of equations. And at the beginning, when I was saying when we set up equations, either PDEs or ADEs, for the previous two models, they were PDEs here, ODEs. And I can tell you the pharmacists, especially medical science, have changed a little bit because always this diffusive phenomena, they believe in that. but pharmacists are a bit keen on using ODEs. They find it easier, and it gives what they want to get. But I end up telling him one day I put up a PDE for this model. I hope I'll do it one day. Okay. I'm very proud of this results because I was part of it. And this is the numerical model, the mathematical model that we end up by this result, this graphic result, which is very meaningful to them. And this is the experimental work that has been done from AstraZeneca, and they had the tables, and we told them if you can see some graphic with colors, because they don't have a lot of colors in their softwares. And thank God to Morzer, and I think Armin Sepp, who is an engineer working in AstraZeneca, who made up this. And I can tell you, because we were just trying adapting their given data, because in this paper, which is published in Taylor series, we have to put all the data was given by them. And we tried until we got what they wanted, because they give us all the data. They want to write to something, but it takes so long. And remember at the beginning where I said the first thing that people are thinking about mathematical model is the cost. It's costly. It's costly in money because they need a lot of experiments to do, and this needs a lot of components, etc. But also, I knew on that time, for the first time in my life, that any medication, any product, in pharmaceutical product, to be put and commercialized, it needs 18 years of experiments before it's approved. But for this work, I think it took us like 9 months to do it, and they adjusted the experiments from this model. Okay, so I attract the attention of the public for the mathematics. They are very useful today. Do you want me to stop here a little bit, or for any questions, or I'll carry on?
Yeah, I think we can make a break if you wish before going to the next.
If somebody wants to ask questions, I can.
Yes, if
at
there
this
is
first part, because I gave brief models with some results.
Please, if there is any question. For me, I have a question. When you have the interaction fluid and bubble for the model, here you have some assumptions on the bubble, and my question is there a possibility to model this phenomena by phase transition, as you have?
Yeah, that's a good question. That's for the multiphasic phenomena, or we cannot have a transition between the two because they are two fluids with completely different aspects.
Okay.
It's not like the water when it's in solid form, like ice. There is a transition. It can be evaporated to be gas. So this we can have transition. But in this case, the cellular is not blood. The blood has a particular density, viscosity, etc. But the bubble, this cell, when we got the data from them, it has nothing to do with these. They have different viscosity, density, etc. So the bubble, this cell is moving in the blood without being mixed or miscible with it. So there is no transition of phase, not like water, for example, that has 3 phases, and you can swap from the solid to the liquid to the gas.
Okay, thank you.
A short question, if I can. For the first model, you have 2 unknowns. I was wondering if the second equation is just used to kind of estimate the value of f on the boundary? Because if you have the value of f on the boundary, you can solve the first equation, right?
Yeah,
So
the system,
yeah,
the
you
whole
have
system.
yes, you have two
They
unknowns.
are all together.
Yes, you have two unknowns. Which one is the most important? You have
Both of them are
okay.
both of them are related. The concentration of diluted oxygen inside the water, because there is oxygen in the atmosphere anyway, no matter if it's polluted as well or not. But this oxygen, when it goes inside the water, there is some oxygen. But this oxygen is unfortunately broken by all these multi-organisms coming from the pollution. It's taken from that, so there is no oxygen anymore. Well, enough, at least enough. And both of them, and also the B, which is the biochemical demand, the demand of the organism to still in life inside the water, inside the lake or some stagnant water.
Please, can you get back to the system, please?
Yeah. This one. This one. You mean this one?
Yes, yes. Thank you.
And both have the same term here, as I told at the beginning. As I said at the beginning, this first and second, they have this term, which is the depletion of oxygen due to the elevated biochemical oxygen demand. Because if you have too much pollution inside that piece of water or this place of water, that means you have what you say, a lot of microorganisms just developed there from the pollution, and it's going to take most of the oxygen.
Yes, well, my comment is the following. Can we see the second equation as a way to estimate the value of f on the on the boundary and use it somehow?
Yeah, of course. I mean,
not the first one.
Yeah, but here, if you want to solve the system, either have this data here and solve it, because we need to have the B and the concentration C. If we don't have it, that's an extra work to do. And the applied science experimentalists, they may be happy to have it for them, because it takes so long and it's so difficult to take the measure for it. But I mean, whether we have it or not, it's always a hard task to get.
And is there a way to get some measurement of F and B?
Sorry, excuse me?
Is there a way to have some measurement of B and C on some point?
No, for B, it's impossible.
Yeah.
It's impossible because it's something related. It's like we don't know it. We don't know how much organisms are in the water to know what they need as oxygen. We don't know.
Okay.
Is there another question?
I am a bit curious for the last model, the antibody, that I mean, you use ODEs for that. Isn't it strange, I mean, to use ODEs instead of PDEs?
Oh yes, even for all the study groups, I used to go and be part of it. The first thing they think about medical science, especially not for industry. Industry, they believe in PDEs more than them because they are engineers anyway. And the medical doctors, they think that everything should evolves in time. They never think that something also change in space, like it fuses, like the diseases. In epidemiology, yes, because they only talk about statistics. So they take the dynamical systems, but they don't know that also the disease, whatsoever it's COVID or whatsoever cancer, it diffuses also in the body in space until we start to work on tumors, and then they don't put they don't take attention. Sorry, put more attention to ODEs, because there is diffusion in space in the tissue itself. It's not only the evolution in time.
It's a kind of quasi-static evolution.
Yes. But with the PDEs, like for this model, I put up the model for them in PDEs, and they only commented on it on the paper we published together, and they said, okay, I mean, here antibodies, they just have these arms just to pick up, you know, or attack the diseases in different ways. But I mean, also there's diffusion in the same arm. Is there a diffusion? And I put this for them. If you go on this paper, you'll find at the end a section on PDEs. Like we suggest PDEs, but we don't carry on that because they were happy to get good results, a good comparison with experiments, because of course they calibrate their model. Usually we calibrate our model with their experience, but we did the other way around because we adapted some parameters from them, and then they gave us what they want. This is the picture they want to get. And I kept, you know, trying, you know, for nights and nights, for days and days, until I got something similar. And then I gave them all the parameters which gave me this result. And then they adapt this, and they got, I think, the bispecific antibody, and they commercialized it, I think, in December 2016. And they were happy with that. So AstraZeneca won, but we did the work for them. It doesn't matter. As long as it serves the humanity, we are happy for it.
Yeah, because I was saying that because typically, for example, for people who are working on cardio, electrophysiology, for example, they use PDEs. I mean,
yeah. I have a paper in 2010, and I didn't put the paper. I thought it was too long, but I talked about that many times in other seminars or conferences. It was a PDE because we are looking of something, a cancer on the tissue of of the heart, and there was some voltage in it, and they were trying to cut every single tumorous cell, but still the patient died. And after the donation of one of the hearts at the end, we tried to work out on that, and we set up the PDE. It's I can send you the link for this paper. It's a report, actually, a big report in St. Anne's Hospital. And you know, it was funny a little bit. I was too naive at that time. I was starting with them, and there were too many. I can tell you now, so for the audience, when they present the work or their problem to ask for help from mathematicians or physicists, there are thousands of parameters. You can never know how many of them. And one of, I don't know, I was saying, oh, I'm going to ask a stupid question. And this guy said, no, say naive, don't say stupid. It's a naive question. I said, how many? I cannot put an equation with these thousands. So I asked the question, in another way. I said, what are the relevant parameters you need? And then we put a PDE for them. And their problem is when they were doing the surgery, they were just burning without thinking about geometry. And that's why the heart signal, when it passed through all the scars, there was discontinuous. And you know how many seconds you need to get the signal passing through all the scars to go to the healthy cells. And that's why the patient, although he was well operated, had a good surgery, had a good medical doctor, etc., but he died. And then, like 6 months, I remember we started the work in September 2009, and we put up this this model like 6 months later, and they implanted a small factory to make capsules, very uniform capsules, so that they can do the surgery. So they don't just burn like that. They have to put something very circular, put it so that it will be very smooth, so the scar will be smooth, so the signal can pass through. Can you imagine that? I mean, medical doctors, of course, I keep saying we cannot replace them, but give them an idea that they can use it in the best way in their form. And said, okay, if it's just a geometry, okay, let's think about doing the surgery in a proper way. But it's PDEs. Mostly now I'm working on PDEs. I just modeling PDEs because the fact of diffusing the phenomena is very important. It has to be PDE. Something changed in space and in time at the same time.
We start the second part, or we continue to. If there is no question, we pass directly to the second part, and we thank very much Professor Nouri for highlighting all these questions, and we pass directly to the second part. Thank you.
Okay. Thank you very much. I'm here for answering the question, maybe clarifying things, because maybe you know things, but there are things you should explain deeply for others. Okay, the second part, as I said at the beginning, okay, I'll just give maybe I took more time at the first part. Just give the models, how we do the things, but I didn't give everything, but there are the papers, you can read them if you want. If you need me, just send me an email, I can direct you. So the second part is modeling cellular systems. That's the main thing for tumors and everything. That's like the basis of all the diseases. From clinical data on we can get clinical data, well, more or less easily nowadays since COVID, because there are more databases which are available online for free. Or if you work in a proper network, you get the database. Of course, it's a little bit secret. You only use it for the work you're doing. So the first part, we are going to put up or set up a 3D system representing the tumor. So we are taking three things: live cells, dead cells, and nutrients. Okay, I can give an example here. People who had a cancer or a tumor, you always go through chemotherapy. Okay, the chemotherapy is the worst thing that happens to the patients after the surgery or whatsoever, because it kills everything. And then they keep telling you, you have to be careful with your food, don't take too much sugar, take too much protein, and the protein also is affected. We don't know the quality of meat nowadays. We don't know anything. They are having also artificial, all these animals are having artificial, they are nutrited artificially, so the human being is affected. So there are too many things. So this first part, let's think about just alive cells, dead cells, and nutriments. And let's say the proliferating, that's the live cells which are divided and proliferating. The tumoral cells which is affected, we cannot do anything, we just wait for them to be died. And also nutrients. And the data would be the rates, the proliferating rate, the death rate, and also some constants that will take into account this divided good cells or alive cells. There are also some constants which also we get from the experiment scientists. The absorption of the oxygen, there is always oxygen. You can see here, I talk about lot oxygen, whether it's in the water or in the body itself. You remember when we had the COVID, we were measuring our oxygen all the time. I don't know, you had this in your finger, people who have been affected really harmfully. And there is always a maximum carrying capacities for these three unknowns. We take this and put up this model, which is a PDE, a system of PDEs, taking the live cells, tumoral cells, and nutrients used. You see here there is a minus, this is dead cell rate. We have to take them out. Okay, if there are dead cells, they are out of the system. And then the rest is just taking into account the maximum of each one in capacity. And as I told you, this is the death rate would be written in this form. You will tell me how, because the biologists also are working their own experiments with some softwares, and they give them some graphs, and sometimes also they give them with Mappl or something, the expression of their functions they need. I would do also the same thing with interpolation polynomial, taking their tables and just find my polynomial and just work out. But I took their function and everything from the data. And then started to solve this, of course, with the initial and boundary condition. Usually, this is the boundary initial values problems. Doing the mathematical analysis, okay, I have to go through the well-posedness, as I said at the beginning. I write this system of these three equations with the initial equation condition in this form, because I need to use operator theory, which is well known in mathematics. Okay, so write it in this way, just split up, take everything from the first equation, or write it down. And then use semigroup theory, because if A is a linear operator, bounded or unbounded, we can apply semigroup theory. I'll tell something later about nonlinear operators. And use the Heliosida theorem, using, I don't know if people are familiar with semigroups. Here we only have to check some properties of this operator. And using Heliosida, we need to prove or demonstrate that A can generate a C0 semigroup. Let's put this down. And also, the second part, or the right-hand side part, F, should also be uniformly Lipschitzian. This is something well known in mathematics, when people who have dealt with strong well-posedness. And then with these two properties, we can end up by having a solution. And even in evolution equations, Morton in 1976 wrote down this solution analytically. Okay, this is for linear operators, and this is a linear operator here, because we can write it this way. But for nonlinear, unfortunately for nonlinear, some people sometimes, even our PhD students, they come with they just, how do you say, it's not copically, it's something like adapting things for the wrong results. When the operator A is not linear, you have to linearize it. There are some tools, mathematical tools, to do it. And how to do that? Just take the maximum of the function, plunk it in the nonlinear part, and you have something which looks more or less linear, because the solution can never exceed the maximum of whatsoever you're looking for. So this for the well-posedness. Just go back to semigroup theory. I think every student has gone through this for his event before master degree, and they know, or they should know, hopefully, to use this. And the Heliosida can say that for A to get a C0 semigroup, it has to be semi-axisymmetric. For in the weak sense, this is we need it for the strong sense. In the weak sense, because we need to solve it. Okay, sorry, let me get back. If you want to get a strong solution, you just use finite differences. But I prefer the weak way because I can use finite elements and because they are more reliable for these problems. Okay, for the weak sense, you just take one, you just multiply by test functions, integrate over omega, And then you get this weak weak formulation of the problem itself. Of course, you have to express every single term. I did it in purpose here in case some PhD students need the transparent or slides later. They can check if there is a little mistake somewhere. Okay, what I did, I just took this system, multiply each equation by a test function, integrate over omega, and then get the weak formulation. Okay. To show, okay, this is classical, and I think a PhD student can know that. If they're working in PDEs, of course, weak solutions, you need just to check some properties of these bilinear or trilinear forms. It depends. These are bilinear forms, but this is a trilinear forms because it takes into account two unknowns with the test function. The continuity, the bilinearity, the trilinearity, the coercivity, and the linearity of the right-hand side, if there is some hand right side. And with this properties, we can show by lax milligram that there is a unique solution for the system. Then going once the analysis analytically, the numerical analysis analytically is shown or is proved, you can go on discretizing numerically. So what we do, we just write down the weak formulation or the discrete weak formulation, which is related to the continuous case. And then, of course, you use on a finite dimensional domain, and then do your triangulation in with finite elements, and for the t, for the parameter or the variable t on the left-hand side, just use finite differences. But the best thing is to use implicit. That is everything that has been semi-discretized by the finite element method should be in time t plus h. So you will be safe to get a stable scheme without any conditions. That's what we call unconditionable implicit scheme. Solving this with this implicit scheme, we get this 3D very illustrative results. And these, as I said at the beginning, when the alive and the nitrogens behave same way. It's like when the NC, the nitrogen cells are decreases, the tumoral cell increase, sorry. Because that means that, like I said at the beginning, the oncologists, when they tell the people, the patients who cancerous patients, or the people with the cancer or the tumor, whatsoever, no matter what, how serious it is, they always tell you to avoid take sugar, because the sugar will increase the tumoral cell. And also if you don't take enough proteins, meat, eggs, whatsoever, also can affect your situation or your state of the disease. Okay, so this is reflected exactly from the experimentalists, from the medical doctors. They say, okay, that's a good result, and your system can predict some results for us. Okay, and also we can also see graphically is more significant, sorry. You see here the blue and the red ones are the alive cells together with the nutrient. They behave the same way. While if this is decreases, I think this is the UP, no, that's UT, the red one, yeah, is decreasing. You see that the tumoral are increasing, and that's logic. And these two results are part of one of my PhD students who is preparing her viva soon. And she was quite happy with that because we tried our best to find the way to show people what's happening in reality with just few equations coming from mathematics. The second part of this deep looking in cellular systems is the confining cells. We have always talked about metastasis, predisposal cancer. It started very slowly, and it was very worse in a few months because there are some cells which are in between. They are not alive and they are not dead, but they're in between, and they are really hiding somewhere, and we don't know where they are. That's what we call confining. So to look at this, part of the cellular systems, we need some requirements, which are shown or seen by the experimental work of biologists. So we can see the biologists say the proliferation on dead cells. If we don't have any proliferation and we don't have dead cells, that's the confining cells, that means that the model should be in a conserved form. So there is a conservation law. That's the physical law we should take into account. And then also, we should have a look of the behavior of the cell fronts because they are moving somewhere. I mean, like the live cells are moving to be dead cells because of some situation. So they make like fronts, like waves, okay, because they're moving, so the shape are changing, so they look like waves. Also, we can get steady states because they can move and then they slow down, so they can get the steady state. That is well known in mathematics. Some other issue would be the biochemical factors, because they're using in small labs. All these experiments are used in small labs in biology. And we can see either they attract or they repel some cells. So from one side to another, from the alive cells or the dead cells, there is an exchange of that. The motility is a terminology used to say that there is a free movement, and usually it's a Brownian motion. That's why at the beginning I said, okay, we are looking for some equations, but either PDEs or ADEs in a deterministic way, but the right way is a stochastic. We haven't done that yet, but it should be in a stochastic. That means you have to need to add a Brownian term or a stochastic term to take this into account. And also taking into account diffusive phenomena, as I was talking earlier about this. Also, the regulation factors also should take into account a certain threshold. I mean, there is a limit. There is a limit if, that's why we say sometimes they say you are at the end of the stage and that, where there's always a limit in the number of cells, especially tumorous cells. And to put this requirements seen by biologists in their experiments in a model, let's start with a basis. One of the bases as an equation or system of equation in this case, especially taking into account some waves, how they say, issue or ideas on waves, is the Keller-Segal system, because it has been used successfully in traffic flow modeling. The traffic flow, that means that there is something moving from a small amount to a bigger amount. Here is from unicellular to a complex structure. So we thought about, okay, this might work. Let's see the literature behind, who used it and for what. Like Kolobov, They've used it in auto wave detection. This is for diseases, detect the auto waves, how they make some waves, especially in heart problems. Some others use it in gradient flow approach. And this we use it in image processing. I think Mohammed Hasham had used. We always control the gradient of the image more than the pixel of the image, because that's what it directs us to change the behavior. We can also predict some therapies, and the work by Brady explained this very well. It's a nice paper, this one, I've read it. And recently we have used some ideas, not the same model, but some ideas in our 3D models I explained earlier, but with variable diffusion coefficients. So when we were looking at this model and we wanted to use it as a basis, we found out that it is a good model, but it cannot produce traveling waves or sharp self-moving fronts. That's one of the main requirements by biologists. So the good thing is to take this model or the system and add a new modeling term. Of course, to modify it in a way to make it work for this phenomenon. So in the Keller-Segal model, it takes a convection term to be a constant multiplied by the density. This is the term, which is the diffusive term or the convection term. But we want to have this front moving with waves. So we try to use a function, a nonlinear function, instead of this a, instead here, and see what's happening. Of course, adapting also everything. The threshold, I was talking about the maximum limit of the cells, of the density, which I call it rho infinity, and then write this system. It's just the same system, but the right-hand side always changes in the Segal model, and also this F. This is what we call the flux. So the flux is designed to attract, as I said earlier in this requirements, attract or repel cells, because there are some clustering regions with denser regions, and some others are less denser. So we want to see what's going on each side. So the choice of this F should satisfy the requirement of the biologists. Okay, so the choice of a polynomial of degree 2 could satisfy this, because they need to see two regions, one with the positive part and the other one going to the negative part. The positive is what they say chemio-attractant, and the other one chemio-repellent, which is this part. And there is always a critical density constant, which should be taken into account. This you could see, I just put this yesterday, I was just plotting something for this function, for this choice to show you how we choose this. It's the simplest maybe choice, which satisfy the requirement of biologists. You have to satisfy the biologist by some graphic results. Okay, we need to see the convecting term and also what they call the characteristic velocity. The characteristic velocity should lead also to some stationary wave. That is the steady state. I was talking earlier about that. And this can be given by this. Okay, once we set up all this, the equations and also some boundary condition and initial value, we have to look at the well-posedness. No, I don't want to repeat everything. So we use a semi-group theory and the same theorem. Of course, we adapt with our given data or all the coefficients we have. Also, for the numerical study, we have to look at the stability in a numerical analysis theoretical way, and then we discretize why with a suitable scheme based on finite elements and finite differences. And I told you why we choose always the implicit scheme, just to be sure if the thing is stable. If something happens, we would think it's from calculation from the machine and not from the choice of our scheme or numerical technique used. Okay, these are the results. Okay, here are the meshing. We just took some, this is the 2D results. We can do it in 3D as well. We start with 3 cells, single cells, which are not close to each other. They're just set in any choice. And then we have to solve to get the solution. And you see here, this is the density. They're just moving until they make this structure. They call a complex structure. It's not anymore these nice circle ones or disc ones. And for the concentration, it just behaved the same way. This is the concentration and this is the density. So here we say, okay, that's a very, it gives us an insight that there is a direct relationship between the concentration and the density. Why for the first one, we just dealt with 3 different aspects of cells alive, dead, and also how we use the neutrino concentration. These are recent results I've done myself. And thank you for your attention and for your patience as well. And these are some references you can use. And if you need any more information, I can always be ready to help. Thank you again.
Thank you very much, Professor Nouri. Is there any question for this second part?
Alors.
So sorry for extending
vous sentez ou non?
more time.
Oui, oui, on vous entend, Monsieur Isao.
Ah. Alors, non, tu peux faire la question.
Yeah, I can hear you.
Alors.
Hello, Isao, how are you?
Bonjour, bonjour. Alors, vous avez fait la liste de exigences de point de vue biologique.
Mm-hmm.
Et puis, vous avez modifié un petit peu l'équation. Et modifié, vous avez fait introduit la fonction f de p, f de rho, pardon.
Oui.
Mais il me semble que cette modification est assez loin de exigences biologiques, parce que exigences biologiques sont beaucoup de plus.
Non.
Donc, c'est-à-dire que votre modèle
oui.
est trop simplifié par rapport à cette exigence de... Oui, ici, c'est un modèle que vous... non, avant, il y a exigence de biologie, vous avez montré.
Ce modèle avec F de rho, il est utilisé pour les données biologiques. Par contre, avec A rho, c'est pour le trafic. Donc, c'est pour contrôler le flux du trafic. Il n'a pas... Donc, moi, ou bien je l'utilise directement et pour faire autre chose, mais il ne va pas satisfaire la biologie. Si je le prends tel qu'il est, il ne va pas satisfaire les données de la biologie.
Non, c'est-à-dire que, excuse-moi, retournez à la page précédente.
Oui.
Non, encore.
Mm-hmm.
Il y a ici. Il y a beaucoup de 6 points d'exigence de caractère biologique.
Oui.
Alors, il me semble que simplement introduire f de rho ne satisfait pas cette exigence.
Mais si, pardon.
Donc,
Ça.
Le
Pour
système d'équation, oui. Migration,
déjà,
par
déjà la loi de
loi de
conservation,
etc.
je vais aller un point par point. Donc, la loi de conservation,
Oui.
le modèle en lui-même de base de Segel, il est conservatif.
Oui.
Pour les ondes
Oui.
avec les les fronts, il n'est pas satisfait avec A rho, où A est une constante. Par contre, quand je change
Oui.
le F de rho, j'ai préféré prendre le graphe, comme je vous ai montré, la partie positive et la partie négative. Donc, j'ai déjà le chémio-attractant avec F positif de 0 jusqu'à rho critique, et entre critique jusqu'à le seuil, l'infini, c'est négatif. Donc ça, c'est vérifié. Le steady state, c'est vérifié parce que on peut pas dépasser le rho. D'accord? Pour le brownien, je n'ai pas pris de diffusion isotrope ici. Je l'ai pris quelconque. D'accord? Donc, j'ai pas d'isotropie, sinon j'aurais que le Laplacien. Donc, je marche pas avec ça. Donc, il y a un mouvement quelconque. Avec le graphe à la fin, vous avez vu, pardon. Vous avez vu. Et puis pour les trucs, les régulations, les facteurs de régulation biologique qui ne donnent un vrai rho, un seuil. Et c'est pour ça que je l'ai pris ici dans le graphe. D'accord? Je l'ai arrêté. Donc j'ai pris des termes ou bien des données de la biologie qui arrêtent le processus parce qu'on ne peut pas au-delà de là, c'est la mort si vous voulez. Donc la tumeur, elle va jusqu'au bout. Et là, c'est la critique. Par exemple, le phénomène change de signe, donc c'est ma fonction que j'ai choisie, qui est simple, mais il a fallu travailler jusqu'à ce qu'elle arrive. Quand vous voyez le graphe ici, vous voyez, par exemple, je peux aller au-delà, je peux aller pour voir une structure un plus compliquée. J'ai arrêté parce que j'ai vu qu'ils sont rattachés, d'accord? Et que la concentration, ça, c'est les facteurs de régulation qui n'ont fait qu'il y a une compatibilité entre les densités et la concentration. C'est la concentration du biochimie qui est utilisée dans les laboratoires d'essais biologiques. Ça, c'est pas sur les malades, ils sont en train de travailler sur des cellules qu'ils développent eux-mêmes dans un laboratoire. Donc, moi, j'étais contente d'avoir quelques données de chez eux, mais la fonction, en la construisant, il faut qu'elle satisfait un petit peu c'est ce qu'ils demandent, les requirements que j'ai mis au début.
Donc,
Pourquoi je les appelle front cells. C'est vrai, parce qu'ils avancent, ils avancent. Il y a pas de changement de shape, comment dirais-je. Il n'y a pas un changement. Vous voyez que c'est très, très conservé. Puis après, ça change. Ici, par exemple, parce qu'ils sont accolés l'une à l'autre, et donc ça change un petit peu. Si je vais un peu plus loin, je vais voir un petit peu. Et vous voyez cette visualisation, this shape and this one, they look almost the same. Ça, c'est les valeurs de la densité, ça, c'est les valeurs de la concentration. Mais l'allure est la même, donc the shape is the same.
Oui, je n'ai pas bien compris. Loi de conservation.
Oui.
La loi de conservation, où est représentée dans l'équation?
L'équation elle-même de Kessel, elle est conservative. Elle, d'origine, elle est conservative. Même si on ajoute un terme ici, parce que là, quand tu as un rho, si rho va jusqu'à l'infini, ça, c'est un terme qui va être un petit peu assez grand. Et donc, là, déjà, la loi, pardon, le modèle de Segel, il est conservatif, pourvu que cette partie-là soit bien définie. Il est
Donc,
conservatif.
il y a deuxième
Il est
membre qui est.
d'origine conservative. Donc, on peut, par exemple, aller vers le moment, chercher le moment de la densité, ou bien, parce que c'est pas des lois conservatives comme KDV, par exemple, dans les ondes. C'est des lois qui ont une infinité de conservation. Mais là, le moment est conservé. L'énergie, elle est conservée. On peut le démontrer. Par l'intégrale de rho au carré, on peut trouver qu'il est conservé. Il est déjà conservé sans que je change cette f de rho. Parce que f de rho, je n'ai pris qu'un polynôme de degré 2. Je n'ai pas pris une fonction. Peut-être, c'est une bonne question. Est-ce que le choix de f d'euro très linéaire, parce qu'il faut qu'elle soit non linéaire pour moi, il faut qu'elle soit non linéaire pour qu'elle prenne en charge le phénomène biologique. Est-ce que si je prends une non-linéarité assez méchante, est-ce qu'on aura toujours la conservation de... Mais là, j'ai quand même, comment dirais-je, respecté la forme conservative du système de Séguel, qui a été fait pour autre chose, il n'a pas été fait pour ça. On l'a pris exactement parce que c'est ce qu'il dit, c'était vraiment le premier système qui a été mis en place pour étudier le traffic flow. Il a été aussi utilisé pour Safa ou Marwa, le Hajj. Donc, les gens qui essaient de réguler le tawaf, on dit ça en arabe, c'est pas. Le tawaf in Mecca, they have used this model because it's pour mettre en place le logiciel de régulation tawaf et Mecca, c'était le modèle qui a été utilisé. Donc, ça n'a pas été pour la biologie. Moi, je l'ai adapté pour d'autres. Ils ont été, il y a d'autres, ces gens qui ont l'a adapté pour la biologie, mais pour autre chose. Pour, par exemple, détecter, c'est toujours conservatif. Là, pour prendre le gradient flow, c'est pour voir un petit peu le changement rapide d'un système biologique. Mais il est conservatif. Sauf si F d'euro,
donc conservatif,
le choix soit non linéaire. Pardon?
En particulier, 12e membre qui règle cette conservation.
Oui, non, mais le deuxième membre, il prend toujours, c'est une fonction qui est dans L2, dont on n'a aucun problème. Elle est second degré en rho. Ça, c'est quelque chose de constant, ça, c'est constant.
Oui.
La même chose ici, elle est linéaire en rho, donc il n'y a pas de problème. Il faut que les données soient au moins dans L2, carré intégrable, pour conserver l'énergie.
Énergie, qu'est-ce que l'énergie ici?
Ah, l'énergie, c'est l'intégrale de rho carré, par exemple. Il faut qu'elle soit bornée par une constante. Le meilleur, il faut qu'elle soit négative, sinon bornée par une constante, pour qu'il n'y ait pas d'explosion en énergie, parce qu'on est devant un phénomène biologique.
Oui, naturellement, c'est simplement naturel.
Oui, mais là, c'est pour ça que quand j'ai parlé à la fin, j'ai dit que pour la stabilité du système, du point de vue continu, du système continu, il faut qu'il soit avec l'énergie, la méthode d'énergie. C'est on multiplie à droite et à gauche, et il faut voir la norme de rho au carré. Est-ce qu'elle est bornée? Donc, on doit chercher les conditions pour que la stabilité soit maintenue. Ça, c'est primordial hein, en analyse numérique. Il faut le faire du point de vue analytique avant de passer aux simulations numériques. Sinon, ça ne marchera pas. C'est-à-dire, si vous voulez, c'est la fonction de Lyapunov. Chercher la fonction de Lyapunov.
Oui, mais c'est lien, c'est-à-dire.
C'est un lien entre les deux, oui. Voilà.
Ouais.
Il y a des gens qui préfèrent dire la fonction de Lyapunov. Moi, je préfère dire la méthode de l'énergie. C'est plus quantifiable du point de vue mathématique analytique et aussi du point de vue simulation numérique. Parce que après, je vais calculer les valeurs propres, moi, du système algébrique. Pour avoir des valeurs propres bornées par une constante. Ça, du point de vue numérique, parce que je ne peux pas, moi, chercher l'intégrale de rho carré, etc. Numériquement, ça va être autre chose complètement, mais c'est lié à l'énergie. C'est-à-dire, si vous voulez, je ne sais pas si vous connaissez von Neumann, la méthode de von Neumann algébrique. Et puis après, chercher les valeurs propres maximales et minimales, il faut que le conditionnement soit borné par 1, ça c'est numérique, on peut le calculer, parce que quand on fait le système discret algébrique, on a une matrice, il faut chercher ses valeurs propres, les valeurs propres max et min, si le rapport est inférieur à 1, là on a la stabilité algébrique numérique. Alors qu'en analyse, il faut faire la fonction de Lyapunov et l'énergie bornée par une constante. Et qu'on ne sait même pas à quoi est égale cette constante. Il faut optimiser, mais numériquement, on sait ce que c'est. C'est le conditionnement, c'est le lambda min sur le lambda max. Mais c'est bien, la question, elle est bien, parce que là, moi, je vais penser aussi à un f d'euro qui est non linéaire, mais avec quel degré de non-linéarité? Ah, c'est non linéaire, mais il est quadratique. C'est une non-linéarité quadratique, qui n'est pas assez méchante quand même. Mais c'est encore plus difficile qu'une non-linéarité linéaire. Déjà, elle est quadratique et elle a donné des résultats satisfaisants du point de vue validation, quoi.
Mais c'est quadratique qui
Oui, c'est
garantit
quadratique, mais
l'aspect
oui,
biologique.
oui,
Donc,
pour nous, les mathématiciens, c'est pas très fort, mais déjà pour trouver un résultat valide avec des expériences, c'est déjà quelque chose. Et on n'a pas besoin parce que les mathématiciens, en général, ils essaient un petit peu comment dirais-je, de fortifier des choses pour les rendre plus difficiles, mais on ne sait pas à quoi ça sert. On essaie de développer des choses, c'est pas
naturellement.
là,
Donc,
mais les expérimentalistes comme Newton, par exemple, depuis très longtemps, il a cherché des méthodes simples et pratiques.
oui, naturellement.
D'accord. Là, j'ai donné
D'accord,
quelque
c'est mieux
chose
comme
de
ça.
bien et qui est pratique. Tiens, parce que pourquoi c'est pratique? Parce que je voulais reprendre un petit
Oui,
peu cette issue de la biologie.
oui, oui. Donc,
Quand
c'est
je leur dis c'est une
cette
fonction comme
forme qui
ça, je leur dis
garantit.
que c'est
Donc,
ça,
cette forme qui garantit
c'est la
pratiquement
traction et c'est la
limiter
répulsion. Ils
la
sont contents.
diffusion.
Pardon?
Parce que F de rho tend deviendra zéro, il n'y aura plus cette diffusion qui a été décrite ce terme.
Oui, mais là, quand ça commence ici déjà, et puis il y a une fonction quand même qui évolue, mais qu'elle revient
Oui,
ici. Mais elle s'approche, ça c'est critique. Pourquoi je vous dis c'est critique? Parce qu'il y a un changement. Il y a un changement de phénomène. Nous, on le voit comme
oui,
fonction. Eux, ils disent, écoutez, c'est rho c est en 20, ça veut dire que tout va vers l'infini.
oui,
Ah, ça, c'est l'infini. Mais eux, c'est pas ça. Ils disent, non, non, on va pas s'approcher de la critique. Ça, c'est une zone critique.
oui. Donc,
Il faut
c'est
pas s'approcher.
important.
On dit, ça tend vers. Puis après, voilà. La deuxième zone qui les intéresse, cette partie-là. C'est-à-dire qu'il y a un rejet ou une répulsion ou comment dirais-je, on va rejeter dans une région qui est la migration, qui est libre.
Bon.
Normally, we attend. If we have another question, if you want, of course.
Maybe, moi je peux m'exprimer en français parce que mon commentaire est lié aux questions de professeur Isaou. Effectivement, il y a deux questions intéressantes. La première, c'est que on a 6 hypothèses qui sont issues de la modélisation. Nous, on a l'habitude de voir des travaux de mathématiques, j'allais dire pures, qui mettent des hypothèses, mais qui sont pas forcément liées à la modélisation. Et donc, la question serait, quel est l'espace, la famille des fonctions f euh, qu'on peut choisir et qui satisfont les hypothèses de modélisation. Donc, quel est l'espace mathématique des fonctions f qu'on peut choisir? Ça, c'est la première question. Et la deuxième question, c'est par rapport effectivement à l'énergie. Bon, l'énergie, c'est une question très intéressante. Quand on a une équation d'évolution, ça peut être la descente de gradient ou le flux de gradient associé à une certaine énergie. Et pouvoir écrire l'énergie associée à l'équation d'évolution, ça donne de la visibilité et de l'interprétation au modèle. Ça aussi, c'est une question très, très intéressante. Voilà. Donc, c'est plus des commentaires que des questions. Voilà.
Tu veux que je réponde ou c'est juste un commentaire, c'est ça?
Oui, oui.
De toute façon, la fonction, c'est entre 0 et l'infini. Bon, l'infini, pour moi, c'est ce rho infini qui est la fin un petit peu du patient, quoi. C'est-à-dire le seuil est arrivé, comme on parle aujourd'hui de métastase avancée, dernier stade, et de 0 à l'infini jusqu'à R. C'est une fonction réelle, donc elle doit prendre, à mon avis, j'espère que enfin, avec le travail avec des biologistes qui sont mieux placés c'est de prendre en compte leur ces deux phases, la positivité et la négativité qui, pour nous en mathématiques, pour eux, c'est l'attraction et la répulsion des cercles, c'est-à-dire où ils rejettent un petit peu les cellules. Et là, bon, peut-être je suis mieux placée parce que moi, je suis passée par une chimiothérapie et on est parfois content d'avoir la chimiothérapie, mais la chimiothérapie peut détruire les choses qui sont saines dans notre corps. Et c'est pour ça que cette partie-là, elle est très importante parce qu'elle tue, certes, les cellules tumorales qui sont éveillées ou qui ne sont pas encore éveillées parce que la chimiothérapie se fait pendant un laps de temps et c'est fini, il y a aucun contrôle après, c'est juste le contrôle de l'immunité pour les cancéreux. Mais elle tue aussi les cellules saines qui sont là, qui peuvent fortifier. C'est pour ça qu'on parle d'immunité. C'est vrai, ils ont une terminologie, les médecins, comme ah, l'immunité tac, talat, l'immunité tac, mais il y a pas de cette explication que nous, les matheux, avec nos, enfin, c'est pas qu'on est plus rigoureux quand on dit que ça marche pas, ça c'est juste faux, mais il n'y a pas de allapropé. Donc, ils n'ont jamais dit aux patients, sauf si des gens qui sont plus, enfin, peu importe votre niveau intellectuel, vous saurez jamais, si vous n'êtes pas en train d'exercer, pardon, le métier peu importe, le médecin ou autre, pour savoir. Ils nous ont jamais dit, il faut pas faire une rupture, il faut faire, par exemple, une chimiothérapie, protocole consécutif, il faut pas s'arrêter et reprendre. Ça, c'est un petit peu, ça fait mal au cœur quand on connaît pas la réalité. Et deuxièmement, la chimiothérapie, elle tue, elle est toxique. La toxicologie, elle reste pendant des années et des années. Il y a des gens qui ont des problèmes je ne sais pas comment on appelle, neurologiques à cause des chimiothérapies. Ben, les gens aussi, ils ont expérimenté le Covid. Le Covid, il a laissé des séquelles et des séquelles. Aujourd'hui, les vaccins pour la, pour la, comment dirais-je, le flou, euh, les vaccins qu'on fait pour ne pas être malade, c'est très toxique. Il y a des effets secondaires et ils ne nous expliquent pas. Donc, on ne peut pas tout savoir. Et donc, moi, je suis contente quand même que les gens s'orientent vers la modestie mathématique parce qu'il y a des résultats un petit peu qui peuvent expliquer les choses, qui peuvent dire ça marche pas. D'accord? On ne peut pas tout faire. Mais on on va pas remplacer ces médecins aussi expérimentalistes pour leur donner. C'est un modèle, c'est pas le modèle premièrement. C'est un modèle qui peut satisfaire certaines conditions des expériences, mais c'est pas le modèle. D'accord? C'est juste un. D'accord? Il n'y a pas d'unicité. Voilà, je vous
Mhm.
remercie.
Juste une petite question et juste une perspective. Est-ce que F, elle peut dépendre de C?
Non, parce que le terme de convective, il dépendra que de ρ. C'est la densité, que de la densité ici. Tentez. Même
Parce que le modèle de Siegel, non linéaire, purement non linéaire, c'est une fonction de U fois gradient de U, en fait.
U gradient de U, d'accord.
Oui.
Mais là, comme il y a une c'est surtout la densité, il veut savoir la densité. Donc, le terme de convection qui infierait la densité. Non, je ne sais pas où est-ce qu'elle est le terme. Voilà.
Ouais.
Donc, dans C, il dépendra que de ρ, mais dans la convection, il n'y a que de ρ. Il peut être allié à une constante ou à une fonction. Là, on a pris une fonction non linéaire juste pour satisfaire la deuxième, troisième
Mhm.
donnée de la biologie. D'accord.
Mais, mais,
Donc,
mais, mais Keller-Segel,
ça, c'est le terme qui va jouer le rôle de, si vous
mhm.
voulez, convection, comme la diffusion, comme, d'accord.
Mhm.
Parce que la concentration, c'est vrai, il y a une diffusion du nombre de cellules, ou bien pour avoir cette structure complexe. Mais la concentration, c'est des choses qui sont contrôlées par l'expérience. Ils mettent comment dirais-je, des produits biochimiques pour avoir un petit peu l'avancement ou l'accrochement, ou le clustering ou la migration.
Mhm. Thank you. Is there another question? No question? Thank you very much, Professor Nouri, for this presentation, and see you soon for another topics, another wide range of mathematics. And thank you very much.
Very much.
Thank you very much to everybody. Thank you for the organizers. It's a very productive, how do you say, events. I hope I'll be there in lively next time, but I have seen the previous ones, and good luck. Try to encourage also young people, even PhD students who are doing well in their PhDs. It would be good to see and direct them. And thank you very much for your patience. I'm sorry to talk about tumors and diseases, but this is nowadays